Students, in this session, we'll talk about a device called capacitor. Have you ever heard about the name of the device capacitor, which is being used in the electrical appliances? Just think about the fan, electric fan. In this electric fan, this device, this cylindrical device, this is actually a capacitor, which is also named as condenser. You would have heard about condenser. What is the role of the condenser here? See, let me quote one example situation. Let's say you all are aware of that when we need to start motion of some body over some surface. Let's say this is a box which we need to slide over this surface. Okay, we need to slide over this rough surface. Then initially to make it to move, we have to apply some force, and when it starts moving, then comparatively a lesser force will work to continue the motion without any acceleration. Similarly, in the same manner, just to start this fan rotating, just to start the fan, initially some more amount of current is required. Got it? Because it requires a torque, and here the torque is provided by the current. Okay, so initially a little large amount of current is required, and once it starts rotating, then comparatively a lesser amount of current will work. Right? So in this manner, this condenser provides actually that additional amount of current which is required which is just required initially. So condenser is basically, or capacitor is basically a device which stores the charge which can be used according to the requirement. Similarly, as you would have noticed the flashlight of the camera, that needs a sudden flash, the moment you click, there is a sudden flash of light. Large amount of light is produced for a moment, for some moment. So there also capacitor helps. So there are many devices, many electrical devices where where we are using the capacitors just to provide that additional amount of current. So how do we define the capacitor? Capacitor is a simple device that can store an electric charge on the plates when connected to a voltage source. So here in this picture you can see these are the various kind of capacitors which are being used in the electrical devices. So it's a two-terminal device. You can see here it's a two-terminal device. There are two terminals. So these are the various kinds of capacitors. We'll study about them in detail. But before studying about these capacitors in details, we need to just need to brush up our concepts of electrostatic properties of conductors, or how do the conductors behave in electrostatic field. So just starting with the first property is the electrostatic field is zero inside a conductor, that we are already aware of. So what is the meaning of this property? That inside the conductor, the electrostatic field is zero. What does it mean? Suppose I consider this is a conductor. This is a piece of a conductor. And conductor means there are the free electrons which are randomly moving here and there. Now, when this conductor is placed in some external field, let's say like this. What does it mean? That here is to the left side there is a positive thing, and to the right side there is a negative, the negativity of this electric field. So what will happen? In this conductor, the free charges, the free electrons will start rearranging. So this is the direction of the external field, right? But inside the conductor, the electrons starts to rearrange, the charges start to rearrange such that the negative charge of the electrons start moving towards the left side like this. The electrons, because on this side we have the positive side of the field, and the positive charges will get settled towards the right side, since negative is moving towards left. So the positive will be settling towards the right, isn't it? Because here we have the negative side of the field. So in other words, we can say that the internal field is set up, right? The internal field is set up, which is opposite to the direction of the electric field. So the electrons keeps on moving till the time this internal field become equal to the external field. So that is how we can see that, yes, in this diagram you can see very well that inside the conductor the electric field will be equal to 0. So outside there is an electric field, and since depending on the shape of the conductor, depending on the shape of this conductor, you can see at every point the electric field lines are normal to the surface of the conductor. So that is how accordingly the external field lines will rearrange. So inside a conductor, even if it is placed in an external field, inside a conductor the electric field is 0. The second property says that electrostatic field lines are normal to the surface at every point in the charge conductor, which is very much visible here also. So again, at any point on the surface, the electrostatic field lines are normal to the surface. So how we can prove it? We have already discussed it in one of the previous classes. Okay, suppose I consider any conductor. Let's say this is a conductor which is being charged, so that the electric field line need to be normal at every point. So suppose at this point I consider like it has to be like this. It has to be normal. Okay. But suppose I consider at any point the electric field line is not normal. Rather than this, it is, let's say, in this direction. So is it possible? So for that we will resolve it into the two components. So there will be some component of electric field along the surface, that can be E cos theta, and because of this tangential component, immediately this electric field will cause the flow of the charge, isn't it? Because there is, let's say, charge Q on the surface, then due to this tangential component of electric field, this charge Q will start experiencing a force from the expression F is equal to QE cos theta, and due to this force there will be the flow of charge which will produce a surface current, but we know that no such current can exist in the static condition. So electric field has to be normal to the surface, to the conductor at every point. Now moving to the next property, the interior of the conductor contains no charge. So as we know that inside a conductor, suppose this is a conductor which is carrying a charge. So the whole of the charge resides on the surface of the conductor, regardless of it is solid or hollow. Even if it is a solid conductor, the whole of the charge resides on the surface of the conductor. And if there is no charge inside the body, it will lead to the conclusion that inside the surface, inside the conductor, the electric field is 0. Right? Now the potential is constant within or on the surface of the conductor. Again, using this concept that inside a charged conductor, electric field is 0. Right? We know that electric field is related to potential as E is equal to dV by dr. So from here we can say if electric field is 0, then V has to be constant, so that we can say that potential is constant within and on the surface of the conductor. The next property says that electric field is 0. Just now we had discussed in a cavity of a hollow charged conductor. So suppose I consider this to be the conducting body, and it's a cavity inside it. So whatever charge we give it to it, the charge will stay on the surface only. The charge will reside on the surface, and inside the cavity there is no charge. And if there is no charge inside the cavity, it means that electric field also need to be 0 inside this cavity. And using this fact, we'll talk about the phenomena called electrostatic shielding. It's a very important phenomenon, according to which electrostatic shielding is a phenomenon that is used to block the effect of an electric field. The effect of the external field on the internal content are blocked using the conducting enclosure. And this phenomena was first of all being discovered by Michael Faraday, and after the name of Michael Faraday, we talk about Faraday cage. So I'll come to this point, but based on this electrostatic shielding, this is it has a very important role in our day-to-day life. And one of the very important application of electrostatic shielding is, during the thunderstorm, we are always advised to stay inside. Even if we are outdoor, then we are advised to stay inside some vehicle, let's say your car or this bus. So what will happen, that if there is some, what to say, if there is lightning and thunderstorm, then it will be safe to sit inside a car rather than to stand near a tree or in the open ground. Because if you are inside a vehicle or inside a car, then the metallic body of the car or the bus becomes electrostatic shielding from the lightning. So whatever charge will get discharged over it will flow over it. So whatever it is not going to harm the person who is sitting inside it because of this electrostatic shielding. The charge will stay on the surface only. And through these conducting, these tires are also somewhat conducting, although they are rubber tires, but some conducting material is always there. So through these tires, the charge is it is being discharged to the ground. So let's talk about the Faraday cage. So what is a Faraday cage? It is an enclosure used to block the external electric field in the conducting material. It is also known as Faraday shield. Michael Faraday in the year 1800 invented Faraday's cage, and he found that when the metal cage which acted as an electrical conductor was charged, the charges appeared only on the surface with no effect on the interior, as you can see in this figure. So you can see it's a metallic cage and a person is standing inside the cage, right? And this cage is being provided with is being connected to the high source of voltage. So even if it is connected to the high source of the voltage, there is a large current on the cage, which is metallic. But since the person is inside, it will not get any shock because the whole of the charges will stay on the surface of this cage only. So that is how this is named as Faraday cage after the name of the Michael Faraday. So one very important application of this electrostatic shielding is, the sensitive components of electronic devices. They are protected or shielded from the external field by placing the metal shields around them. So this is somewhat the metal shield, we can say. These are the metal shields inside which we can keep the small components of the electrical devices. So they will not get damaged in the presence of some external field, right? So these are some of the important examples of electrostatic shielding, and based on the properties of this conductor's behavior in electrostatic field, now we'll continue our discussion with capacitor or the capacitance. So first of all, we'll talk about the electrical capacitance. Now, what is this electrical capacitance? This is again the ability of the conductor to hold the charge. As we talk about, capacitor is a device that holds the charge. So electrical capacitance of a conductor means the capacity of a conductor to hold the charge. Okay. So what does it mean actually? For this, again, I quote one example. Suppose we have a beaker. Suppose we have a beaker. This is a beaker. Okay. Now, suppose you pour some water into this beaker. You pour some water into this beaker. So the more water you just pour into it, the more will be the level. The water level will rise. So that tells the capacity. That tells the capacity, or how do we talk the capacity of this beaker? The capacity means how much amount of water it can hold. The more the amount of water is, the more will be the water level, right? Similarly, if we talk about some isolated conductors, suppose this is an isolated conductor, and you just provide the charge to it. You just keep on providing the charge to it. Then what will happen? It will hold the charge, right? So the capacity to hold the charge is called the electrical capacity. Okay, how much charge it can hold, right? Like in case of this beaker also, if you go on pouring the water into it, then what will happen? After a certain limit, it will overflow. Same will be the case in a conductor also. If you go on giving the charge to it, then the charge, after a certain limit, the charge is going to overflow. Okay, so what happens when we provide the charge to the conductor, to this spherical conductor which we have considered? The more you provide the charge, the more will be the potential level. So that we can say that The more the charges, the more will be the potential. The more the charges, the more will be the potential. Q is proportional to V. So if charge Q is put on an isolated conductor, it increases the potential by V, suppose. And then we can say Q is proportional to V, or to remove the sign of proportionality, we use a constant called C here, where C is called the capacitance. Where C is called the capacitance of the conductor. So how do we define this electrical capacitance? The electrical capacitance of a conductor is a measure of its ability to hold the electric charge, and it is a constant for a given conductor. It do not depends upon the charge. Like suppose I talk about this beaker. So does it capacity to hold the water depends upon how much amount of water we are giving to it? Exactly not, isn't it? So similarly, it do not depends. You here C is equal to Q upon V. So we cannot say the more the charge is, the more will be the capacitance. Why? Because the more the charge you increase, the more the charge you give to the capacitor, to this conductor, the more will be its potential level, so that the ratio remains constant. So that is how we define electrical capacitance. So the capacitance of the conductor is defined as a charge required to increase the potential of a conductor by unit amount. How we can define it? Like using the same expression, C is equal to Q upon V. Now here we can say that if V is equal to 1 volt, then numerically C is equal to Q, or the capacitance of a conductor is equal to the charge that is required to increase the potential of a conductor by unit amount. Right? Now let's talk about the unit of capacitance. The SI unit of capacitance is farad, or again after the name of the scientist Michael Faraday, it is named as, just to honor the scientist, it is named as farad. The SI unit is named as farad, or the derived unit, how we can express it? From the formula again, C is equal to Q upon V. If Q is equal to 1 coulomb and V is equal to 1 volt, then capacitance is said to be 1 farad. Or in other words, we can say that the capacitance of a conductor is 1 farad if an additional charge of 1 coulomb increases the potential of the conductor by 1 volt. Right? Or else we can say that 1 farad is equal to 1 coulomb per volt. So, but 1 farad is a very large unit of capacitance. So for practical purposes, we use some small units, some smaller units of capacitance, and they are millifarad, where 1 millifarad is equal to 10 to the power minus 3 farads. Then microfarads, this is microfarad, where 1 microfarad is 10 to the power minus 6 farad, and 1 picofarad is 10 to the power minus 12 farads. So these are some smaller units of capacitance. So in the next class, children, we are going to continue our discussion with the capacitance of an isolated spherical capacitor, and we'll talk about the various kinds of capacitors.